All right, we are on chapter 9, section 7, and we're going to talk about how pH and pKa relate to drugs that we prescribe to patients. So if we look at the pH of a particular solution, and then we have a substance, that substance is a weak acid. So it has a pKa. So remember that weak acid is in equilibrium with its conjugate base form, right? So depending on what pH the solution is, then it will tell us, is our weak acid really in the acid form, or is it in the conjugate base form? And so if you remember when we talked about different kinds of pharmaceutical drugs, we talked about whether the molecule had charged functional groups so that they were more soluble in aqueous solution. Well, that's great that they're soluble, but how are they going to enter the cell? If they're charged, they're not going to want to go across the cell membrane. We want something non-polar in order to get across the cell membrane. And so if we want to get them across the membranes and basically into the bloodstream, then we're going to have to turn them into the non-polar conjugate base form, right? So if we look at one example of a drug, this is a drug for high blood pressure. What we can see is that this drug has a pKa of 9.4. So when the pH is lower, over here, and the pH is lower than the pKa, what that means is more of the drug is going to be in the acid form. If it is higher than the pKa, right, then more of it is going to be in the base form. And so there's a range, right, from all the different pHs. And so when you're lower than that pKa, you got way more in the acid form. You have some conjugate base, but way more than the acid form. And as we increase our pH and get close to that pKa, more and more and more and more turns into that base form. So if you think about this is a drug that you take orally, it goes down your esophagus into your stomach. Your stomach has a pH of about 2. Right? Very, very acidic. So most of it is going to be in the charged acidic form over here. Well, that's great because it's soluble. That's good. But once it moves into the small intestines, our pH rises dramatically and we're closer to pH 8. So what that means is more of our substance is going to be in the base form. And so this base form is then able to move across the intestinal lining and go into the bloodstream, which is exactly what we want. So this fits with Le Chatelier's principle that we talked about before, right? If our pH is lower than our pKa, then we know that we have more of that H plus or that hydronium H3O plus present, and that's going to shift our equilibrium to produce way more of that acid. But if we raise the pH and we get it higher at or higher than the pKa, then there's going to be less hydronium present and we're going to be having more of that conjugate base present. So the pKa and the Ka tells us the strength of our weak acid and how much of it is really disassociating to form the conjugate base, right? So those two pieces of information are really, really important. And the pKa values don't change. They're constants for a particular temperature. And basically we're only worried about physiological temperature, right? But in contrast, our pH can change, right? We went from the stomach to the intestines and we changed a lot. So a lot of times when we do this, if we can find the pKa and we know the pH of wherever that substance is going to be, we're going to put in a weak acid or a weak base group so that you can have both the acid form and the base form. You can have something that's soluble, but then you can have something that will diffuse into the membrane. And so it's really important for our pharmaceutical drugs to have both of those things. Sometimes it's really important to actually calculate the ratio of conjugate base to acid. And so you can use a modification of the equilibrium expression, and it's called the Henderson-Hasselbalch equation. And I think this one is given to you on the sheet. If it's not, I'll of course give it to you. But you can use this formula to actually calculate the ratio of how much conjugate base to acid you have. So this is usually what we don't know, and this is what we are solving for, right? So if you remember, the drug that we talked about earlier has pKa of 9.42, right? And if we put it into the stomach at pH 2, right, we're going to find that the ratio of our conjugate base to acid, right, is really, really small, which means that we have lots of acid and not so much base, right? And so this number is going to be very small. So you're going to find the acid form, which is the polar form, which is soluble in the stomach, which is great, right? And so then you can also look maybe in the liver, right? And the liver is about pH 7.5, something like that. And so we're getting closer to that pKa, and so we end up having more in the base, the conjugate base form, than in the acid form. And so you can actually see that change. Okay, let's go and do a few quick problems. All right, so we are looking at our practice problems here. For the relationship between pH, pKa, drug solubility, and diffusion. All right, so we have a medication. We have an anti-hypersensitivity medication, and it's shown as an acid right here. So this is our acid. The pKa is 9.6. Which form is charged? Acid, conjugate, base, or both? Well, I'm being told that this is an acid, right? And then I see, look at my nitrogen here. My nitrogen is charged. So what form is charged? If you draw it and we say, hey, it's an acid and it's charged. So that's acid. That's just looking at it and telling. So which form will predominate in a stomach with a pH between 1 and 3? So we're going to say pH is equal to 2, whatever it is, doesn't matter. Our pKa, we just pick something between 1 and 3. Our pKa is 9.6. So remember our rules, right? If our pH is lower than our pKa, right here, pH is lower than pKa, what's going to happen? That's going to mean that our acid form predominates. So which form is going to predominate? That's an acid. Which form, conjugate acid or which form acid or conjugate base will be able to diffuse through a cell membrane? Well, if in the acid form it's charged, it's not going to be able to go through the membrane. It's not going to happen. And so what you're going to need is to change it to the conjugate base before you can diffuse. So we need the conjugate base because it is neutral, because conjugate base is the neutral form, right? Form. Okay, so let's go down. All right, consider our vitamin, which has a pKa of 4.85. So will the acid or the conjugate base predominate at the following pH values: 3, 4.8, and 7.4? Okay, so what I'm going to do is I'm going to create myself a little table of the 3 different pHs: pH 3, pH 4.85, right? Yeah. And then pH 7.40, and kind of answer each of these questions at those pHs. So A says, what will predominate? Is it going to be acid or conjugate base? So if we're at pH 3 is lower than our pKa. So here our pH is lower than our pKa. If our pH is lower than our pKa, that's going to be the acid form. Okay. Now B says at each pH, is that form charged or uncharged? Because we're lower, right? And we look at our structure here, and our pH is lower than our pKa. What we're going to do is we're going to be seeing the uncharged version of our substance here. And then C says calculate the ratio of conjugate base to acid present at each pH. Well, this one is the Henderson-Hasselbalch. pH is equal to pKa plus the log. Remember, you got to put the conjugate base on top and concentration of the acid on bottom. So we're going to solve for this ratio. Okay, so we're going to say our pH is 3. Our pKa is 4.85 plus the log of the ratio, right? And so subtract 4.85. And then you're going to have to take the inverse of the log, right? So you get, I didn't even do this one beforehand, 4.85 3, so that gives me negative 1.85 is equal to the log of the ratio, right? And so we take the inverse log. So we say 10 to the negative 1.85. So if you do that, what you should get is 0.014. So that's C, right? So we did everything for pH 3. So this is our ratio. And if there's nothing over it, you can just say it's over 1, right? So we can say we have a lot more acid than we do base, and that makes sense. Okay, now what if we're at pH 4.85? Oh, here our pH is equal to our pKa. If your pH is equal to your pKa, by definition, that means you have equal acid and conjugate base forms present. So then you have equal amounts of charged, or GED, and uncharged. So then we can go in and plug this into our formula, and we can get the same, you do the same process, right? You just put here 4.85, right? So when you plug that in, let's see if I can kind of separate the two, you should get 1, okay? Then if we're at 7.4, here our pH is greater than our pKa. If our pH is greater than our pKa, we're not going to have a whole lot of the acid anymore. We're going to have lots of conjugate base. So this is going to be the charged version. And if you put those numbers in, what you should get out is 354. And if you want to put them over 1, you can, right? But so that's telling you that you have way more conjugate base, because the top is conjugate base and the bottom is the acid form. So you have way more conjugate base than acid, okay? All right, here we go. Procaine and lidocaine are used to numb the gums during dental procedures. Procaine has a pKa of 9.1, whereas lidocaine has a pKa of 7.9. What do you think will relieve pain faster in the gums? And explain. So what do you think? Pause and kind of think about this one. It really should be lidocaine, right? In both, so in both, we have a pH that's less than our pKa, right? So what does that tell us? That tells us, if you look at the comparison, right, though, you say pKa of procaine and pKa of lidocaine. Well, what's our pH? What pH are we at, like in our gums? We're at about pH 7, very close, pH 7. Like 7.3, 7.4, something like that, right? So if you look at lidocaine, lidocaine's pKa is really close to that. So since lidocaine, L-I-D-O, since lidocaine's pKa is close to the physiological pH, right? Then there's going to be more of our conjugate base form. And remember, our conjugate base form is neutral. So guess what? More of it is going to cross the cell membrane. More will cross cell membrane. Ooh. Right? And if you're crossing the cell membrane, then you're going to be active. You're going to be having an effect on those cells. And so that's what makes drugs effective at certain pHs. All right, have a good rest of your day.